All right, good evening to our online component and to everyone who made it out here tonight on this wintry morning. Okay. I thought I'd take a few minutes just to, I've had lots of questions about the final project, and so I thought I'd relay some of the things I've talked about with students individually to everyone in the class and give everyone a chance to answer any more questions that they might have right now. First of all, I have expanded my hours that are available by appointment this week. So I'm available into the evening on Tuesday and Thursday, and for most of the day on Tuesday, Thursday, and Friday. So if you do have questions about your project that needs some individual attention, please don't hesitate to ask. There's a link on Blackboard and in the syllabus where you can just directly make an appointment, and we can discuss by Hangout, Skype, in my office, or by phone. So some of the things to clarify are that the presentation date, first one, presentation date is next Monday. Everyone, but I believe one person asked to present tonight. Is that person still here and you still want to? Okay, okay. So we'll get a dry run tonight. You can get an idea. Yeah, and you can get an idea of what to expect. We'll do it later when Tony is here as well, so we'll do that towards the end of class, I expect. But for everyone else, it's going to be next week. So once again, the presentation, there will be easels and boards. I don't actually have one tonight, so we might have to improvise a little bit for your presentation tonight.
Yeah, we'll figure it out.
Yeah, we'll figure it out. But they'll be set up in person. Most likely, you will prepare your presentation in PowerPoint or in Microsoft Word and just print it out on something like 8 to 10 sheets of paper so that we can post them up on a board. And for all of these, there was a little bit of confusion, and I apologize for this, about the preliminary submissions. Those are just intended to be parts of your final project, not something additional, just to keep you on track for doing your final project. So it's not like you have to write a separate report or something. You're just preparing this poster presentation and submitting components of that for peer review. Yes?
I remember at one point, I think Tony had shown us some examples of the past submissions.
Mm-hmm.
Would it be possible to either like see those again or maybe have them put up just so that, I don't know, I'm really bad like when it comes to like visual stuff.
Right.
So I think it might be useful just
to have a demo. Okay, yeah. I think so. Yeah. I can dig a couple up and take the names off, and you'll see one today as well. And I'll give some commentary on it. I will be a little lenient on you because you're the guinea pig for the whole class. But it'll be a good way to talk about a presentation and if there's anything that you should mimic or do differently. Okay. Are there any questions about your final projects? There are lots of people doing the community health study flu shot one, and so I guess I've talked about sort of what analysis to do for that a few times, also for the Ebola one a few times. And I think those projects, they all will probably be pretty similar, and the basic outline of a community health study flu shot one is, and I mean, similar for a lot of different projects, but is, you have a page or so of introduction where you mention the background on why this is worth studying and what is already known, and mention like what you're going to do in your project. 1 or 2 pages for an introduction. Again, everything is like large font. I forget what the recommendation is in here, but it's big. 36 point font, because the point is that people are going to be standing from like, this far away, and they need to see it. So it can't be like 12-point font, or else nobody can read it. But it means less writing for you. You can only fit a handful of bullet points on a page, so you have to be pretty sparing with your words, probably not use complete sentences, just enough words to get your points across and give you something to look at and give yourself cues when you present it in 3 minutes. So then a methods where you say what software you use. You can even say what routines in the software you used for the different analysis, what statistical methods you used, and maybe just a short bit about the methods of the study that produced the data you're using, just so that readers will know what kind of study it was and what kind of data you're analyzing. And a descriptives, where I think there's a link in here. Almost always this should just be like, so there's a link here. You can also Google epidemiology table 1, epidemiology table 1, and look at the images. There's plenty of examples. These are more complicated than what you need, but something like this, a column with the variables and their levels, and then one column, a column that has both the counts and the percentages. And that's all you need for the descriptives. I really don't recommend that you do bar plots and pie charts and a bunch of other things for the descriptives, because they don't add anything to this table. It's compact, it's easy to read, it's familiar. Every epidemiology paper has a table like this, so you might as well get used to making it and try to make it look nice and readable, and don't do a bunch of other stuff. Okay, sorry, descriptives, methods, the results. Here, you should try to have at least one figure. So for the community health study, where you're testing a relationship between categorical variables, a stacked bar chart can work well, where along your x-axis you have the different exposures that you're interested in, and on the y-axis the percentages of yes and no receiving flu shot. It's a pretty easy way, or a pretty interpretable way to visualize this. Or say the Ebola study, you have time series data, you might want to draw lines showing the incident rates and fatality rates in each of the country as an XY line graph work well. And also in your results, so you have graphical presentation, also results of any hypothesis tests. So for flu shot, probably you can have odds ratios, giving the odds ratios compared to a reference group. If it's a categorical variable, you'll have multiple odds ratios compared to one reference group, along with confidence intervals. You can have a table of those. And if you can make inference from your odds ratios, you don't really have to have a chi-squared test. If you wanted to do like an overall hypothesis test for a multi-level categorical variable, then you would have to do a chi-squared test, because with the odds ratio, you can only do it for a 2x2 table, so like one group against the reference group. So odds ratios and chi-squared tests are your sort of go-to statistical methods for a pair of categorical variables. For something like the Ebola data set where you have proportions, so there was a question about the case fatality rates, like what percentage of the cases were fatal. You can compare one country to all the rest using a test of two proportions, which we learned in class. Like, do that with calculators, probably easier than trying to do it in SPSS, where you can estimate, you have your proportions, you estimate your standard deviations of the sampling distribution of proportions, the standard errors, and you can get p-value on the null hypothesis of those proportions being equal. And you also have methods for a single proportion of reporting a confidence interval on that proportion. And that one is different because you're talking about comparing proportions. You could do that also for that matter for, I guess you could do that as well for the community health study, except there it really is more about you're interested in the odds ratios, whereas there isn't really an exposure variable in the Ebola data set, which is why I just talked about comparing proportions. So your results has some graphical presentation. Whatever you're doing, try to have some graphical presentation of your results. It adds something. Don't just, if you have time, don't just use the default SPSS output. They have horrible looking, unreadable axes. They tend to have lots of text, unnecessary text in like 8-point or font or something like that. You can change all of that in SPSS before you export it and put it in your presentation, so you can have 36-point font for your axes, the numbers and the labels as well. Yes?
If your data set has like a bunch of missing variables and stuff, do you just leave them in descriptives and then you can do your results with just those that are valid?
Yeah, if you have a bunch of missing data, that they should be in your descriptives, and then I would probably, you can either remove them or you can analyze them as their own category. It depends on how advanced you want to get. You don't have to analyze them. You could probably get some idea of whether they're informative or missing at random just by their, the prevalence of missingness in your different categories. And then you should probably mention something in your discussion about missingness as how much you think it might have impacted your study. So at the very least, they should be in your descriptives, and in your discussion, mention any assumptions that you made about the missingness. Like most likely you would just assume that they're missing at random and you don't analyze them, but that may be a limitation of your study.
And I have one more question.
Yes.
It's specific to mine, but I think it could be relatable to anyone who has categorical variables. So mine it's not 2x2, it's like 2x3.
Mm-hmm.
So I'm wondering if, for the purpose of this, I should just make it to, I should just analyze 2. Or there's a way mine where I can, or should I try to analyze it 2x3?
Yeah, you don't have to get rid of one of your categories. So I mean, that does come up in all kinds of analyses, like the community health study. Yeah. There are some people looking at differences in flu shot unit utilization by age groups or by race and ethnicity. And the two things you can do, a chi-squared test, it doesn't matter how many categories they are, and with odds ratios, you just have to pick a reference group. And and then calculate the odds ratio for each other group relative to the reference group. And you can get that all at once in SPSS with a logistic regression. If your y variable, hi Tony, talking about the final project. If the y variable is binary, so if that if that y1 is binary and it's an independent x variable that is categorical, you can just put that into a logistic regression and get odds ratios and confidence intervals for each of the levels. Otherwise, if you're going to do it by crosstabs, I'm not sure offhand if you actually have to filter one at a time and do your crosstabs, or if crosstabs will give you all the various combinations of pairwise odds ratios. But statistically speaking, it's not a problem. You just have to choose a reference group. So in your results, there's the graphical presentation, the results of any hypothesis tests, and bullet points where you interpret your results. So you kind of walk your audience through and just tell them how to interpret your graphs and your hypothesis tests. Your graphs, of course, should have captions on them, like figure 2, colon, and the title of it, and you can put that interpretation in the caption of your title. Different people do it different ways. Some people like a very descriptive caption, and put their interpretation in the caption. Some people prefer to just have a minimal title under the figure and then have more of the description like separately in the results. They're both acceptable. I won't tell you which one to do. I myself tend to have descriptive captions, but it's certainly different schools of thought about that. And then the discussion is where you summarize your findings, put it in the context of the other, what else is known that you introduced in your introduction, discuss any limitations and any implications for public health policy or anything else. And I didn't mention on here, but you might also want a section for references. If you've cited references, you can put them at the bottom of each page where you cite them, that's fine, or you can have a section at the end for references, I don't care. Any more questions? Okay. And yes, there will be awards, so keep this in mind as you're preparing for the best overall poster, the most interesting topic, and the best poster design. And I can confirm that the prizes have arrived. They are in my office. They are awesome statistics-related comic books and other things. So, so I'm looking forward to it. If there are no other questions, I'll go ahead and get started on multiple regression. Are there any questions online? Now is your chance. Let's see, where is our YouTube page? Probably going to give me some feedback. Our YouTube page. Don't see any. Probably going to give me some feedback. Our YouTube page. Would you keep an eye, Tony, on the YouTube page in case there are any questions? Probably going to give me some feedback. Our YouTube page. If there's any questions on our YouTube page. An eye, Tony, on the YouTube page in case there are any. Okay. Probably going to give me some feedback. And YouTube page. If there's any, no, I mean like during the class, we have 11 people watching remotely. Tony, on the YouTube page in case there are any. Okay. Probably going to give me some feedback.
YouTube page.
No, I mean like YouTube, but I probably won't unless remotely. Yeah, okay. I heard from a few students who want to try to get the subway system. I probably won't unless remotely. Yeah, okay. I heard from a few students. So it's our last lecture tonight, and I'm going to give you just your briefest introduction to multiple regression things. So it's our last lecture tonight, and I'm going to give you virus 1 and virus 2, just a couple of from chapter 7 of your textbook. It's our last lecture to go over regression, ANOVA tables, and predictor variables, linearity, chapter 7 of your textbook. It's our last lecture to go over regression, ANOVA tables, and predictor variables, linearity, chapter 7 of your textbook. So recall back for two variables, we have a response and a predictor, where we put the response on the y-axis. For two categorical variables, back for two variables squared test, we have a response and a predictor, observation on the y-axis. And for don't really count this in this variable, back for two variables squared test, we have a response and a predictor, observation on the y-axis. For don't really count this in this variable, back for two variables squared test, we have a response and a predictor. The response is continuous, and the predictor was categorical. We used the t-test for inference on this, and continuous binary predictor categorical ANOVA for categorical predictor. Test for two groups and ANOVA for multiple groups, and use box plots and binary predictor categorical ANOVA for categorical predictor. And they're both continuous. And scatter plots, we have the R squared and and they're both continuous today to scatter plots for regression, where we again have a response y, but instead we're going to have multiple. They're both continuous today to scatter plots for regression, where we again have a response y, but instead we're going to have multiple. Let's start with an example. They're both continuous today. Oh shoot! That's because I had opened YouTube. Okay, you should be able to hear me again. I apologize for that. Thumbs up. Can everyone online hear me again? I'm glad you were checking.
It's good now.
Okay, good. I probably don't need to go over the review again. I thought this is useful to have in your notes, just as a bit of a lookup page for the different methods that we've used throughout the semester. So I'll just go into multiple regression, which is for the instance where we have more than one predictor variable. And this is super common in epidemiology, where you have usually one predictor that is the so-called exposure of interest, and then you have other ones that are considered as potential confounders or mediators or other variables that may have a causal impact on the outcome. And multiple regression is the most traditional way of doing causal inference in epidemiology, where there is an exposure and other variables of potentially causal impact. There are other reasons to do multiple regression as well for prediction, and simply for identifying associations simultaneously by multiple potentially causal variables. So I'm going to start with an example here where there is definitely a causal relationship between multiple variables. And this example is the weight of books. And I have here 3 predictor variables. So my response variable is going to be the weight of the book in grams. My predictors here are going to be the length, width, and height, and the type of cover. So I'm just showing here the volume in cubic centimeters. But clearly, soft covers and hard covers will have different weight because hard covers are heavier and the dimensions of the book are each going to matter and contribute causally to the weight. So it's a nice example that way. I got the idea from the book. I can't claim it myself. But we're looking here at a scatter plot just of volume of the book in cubic centimeters against the weight of the book. So a simple linear regression. And there's a nice linear relationship. Makes sense. How would you interpret the slope of this linear regression? What is the slope?
Positive.
Sorry?
Positive. Density.
It's positive. Yep.
Density.
Yeah, the slope is its units are going to be in grams per cubic centimeter, and it's the density of paper. So, more questions. So which of the below is correct? So the slope here is this, this density is 0.7 grams per cubic centimeter. The intercept is 108 grams. And the R squared of this simple linear regression is 0.8, or 80%. So this will be a little bit of review about our last, about the last class as well. So the weights of 80% of the books can be predicted accurately using this model, true or false. Give me a thumbs up if you think it's true. Give me a thumbs down if you think it's false. Go like this if you're not sure. Okay, that's fair since you had the online only class last time, but the definition of R squared had to do with the sum of squares of your predictor divided by the total sum of squares. So the variance in your predicted y's divided by total variance. So going back to our analysis of variance tables, we decomposed the total sum of squares into a sum of squares of our predictions from each variable and a sum of squares of the residuals. So if we have a perfect fit here, if all of these data points fell along the line, then 100% of the variance in our data would be explained by the predicted y's, and that would be an R squared of 1. Whereas, if this line were perfectly horizontal, so that the prediction were the same for every data point, then all of the sum of squares, the residual sum of squares would come from residuals. All of the variance would be due to residuals. That would be an R squared 0. So R squared, you can think of as the proportion of the total variance that is explained by your model. But this is just goofy. That's not true, that the weights of 80% of the books can be predicted accurately. I mean, you look at this, they're all predicted reasonably accurately. and there doesn't seem to be any particular pattern as to where they're predicted more or less accurately. It's a good fit. There's some random variation around this fit, probably due to different types of paper. Maybe some other things about the book besides just the volume. But this R squared of 0.8 means that 80% of the total variability in the book weights can be explained by this model, or by the variability in the predictions of this model. Only 20% is left to random residual variation. Okay, how about B? Books that are 10 cubic centimeters over average are expected to weigh 7 grams over the average. So 10 cubic centimeters more, so the average is somewhere in the middle here. A book that weighs 10 cubic centimeters more than that would be expected to weigh 7 grams over the average. Thumbs up?
Sorry.
Okay, thumbs down? Not sure?
I don't know yet.
Okay, so this is a question about the slope and the interpretation of slope. So the slope here is 0.7 grams per cubic centimeter, and it is how much of a change in weight you expect for a unit change in volume. So this says that for every 1 cubic centimeter increase in volume, you expect a 0.7 gram increase in weight. Or for 10 cubic centimeters increase in volume, you expect a 7 gram increase in weight. So this question is maybe it's a bit of a trick question, only in that it's kind of specific. It doesn't matter if it's over average or if it's over, an increase in 10 cubic centimeters from any starting point means you expect an additional 7 grams of weight. That's the density of paper as estimated by this model. So that's true. B is true. Let's see if I can write here. So this is no. This is yep. Okay, C, the correlation between weight and volume is R equals 0.8 squared, which equals 0.64. True or false? False. Let's see those thumbs. Boy, you're a non-committal bunch. I've seen one up, one down. Don't be embarrassed. It's fine. I'm not judgmental. I don't care if you get it wrong. That's why we're here. Okay, well, only 2 people have an opinion, or 3 people. So, in fact, the relationship between the Pearson's correlation coefficient and R squared was that the square, so if that's Pearson correlation coefficient, the square of it is also equal to R squared. So the Pearson's correlation can be positive or negative. R squared is always positive. Pearson's correlation varies between -1 for a perfect negative correlation to +1 for a perfect positive correlation, 0 for no relationship. R squared only varies between 0 for no relationship or no linear relationship, same with Pearson's correlation, and 1 for a perfect relationship. So the correlation, this really should not be capital R. This should be a little r. It's a little r for what's estimated from a sample. And sorry, this, I should not really use rho here because rho is for the population, whereas r squared is estimated from a sample. And you remember we use Roman letters for things estimated from the sample. So this is little r squared is equal to big R squared. And so little r is equal to either plus or minus of the square root of r squared. Sort of looks like an r squared, right? So this is false. It's not the square of r squared, it's the square root of r squared. So it could have been either the positive or the negative of the square root of 0.8, but it's the positive because we can see here that it's positive. So C is false. Yes?
I wrote something that doesn't make sense. I think I was looking and hearing at the same time. For going back to the one above it, the books that are 10 centimeters, well, you said for every how many centimeters means it's expected to go up 7 grams?
So going back to B, for every 7 grams increase, or sorry, for every, either way, every 10 centimeter increase in volume, we expect a book to be 7 grams heavier.
Okay.
Yeah. Yeah. That's the slope is the change in the y variable, which is weight, per unit change in the x variable, which is volume. So C was wrong because the correlation between wet weight and volume, and I could make this more specific and call this Pearson correlation. PEA, I could write RSON is equal to the square root of big R squared, which I don't know what the square root of 0.8 is, but it's going to be pretty close to 0.9, just under 0.9. So this is a Pearson correlation of 0.9. That's a trick question there. That's kind of an annoying one. Okay, D. The model underestimates the weight of the book with the highest volume. So where's the book with the highest volume? That one. So the question is, does the model underestimate the weight of this book? No, it overestimates. Good, finally some like conviction here.
That one was like
What's that?
I think that one was like
the easiest one, yeah. Okay, so they were being sneaky here. I took these from the book. Only 1 out of 4 of them was actually true. Very dishonest. So that was a proper review of linear regression and R squared and the Pearson correlation. That's really the essentials of all you really need to know about linear regression. Maybe not quite all, but pretty close. So this was just because I thought I'd do this myself. In R, I'll show you the output. You can do that. You would get something similar in SPSS, but this is the output of a regression table. This is for a simple linear regression table, but it's going to be pretty similar for all kinds of regression models you use, from like simple linear regression to multiple linear regression to logistic regression and survival analysis, and you won't believe how many times you're going to see a regression table that looks like this. And the key things that it's providing here are estimates. That's another word for the slope. It's an estimate of these coefficients for the intercept and for our variable volume. There is a standard error for each of them. So standard error is our sampling standard deviation. So this is the standard deviation of the sampling distribution. So you can kind of tell this comes from, it's affected by the variability of individual book weights and by the size of our sample. So if we had taken twice as big of a sample, this would be about half as big as these standard errors. There's a t-value, which is estimated for each of the coefficients. And for linear regression with a continuous outcome, this turns out to be t-distributed, and it's something that the software is then using with a t-distribution to perform hypothesis tests on each of these variables. So the intercept, with its estimate of 107 and standard error of 88, this is not statistically significant. Our null hypothesis here for each of these is that the true coefficient in the population is equal to 0. So we can't reject that possibility that the true intercept for, if we were able to look at all books, would be 0. That would mean that a book with 0 volume has 0 weight. Seems kind of reasonable. So maybe this is, this is just normal sampling variation. We certainly can't rule that out. And then our slope, which was 0.7 grams per cubic centimeter. This, on the other hand, has a small standard error, large t-value, a small p-value. So someone want to tell me what that means for our estimate of the relationship between volume and weight? Just put it into normal language, no statistical language.
Volume increases, the weight.
Sorry?
When the volume increases, the weight significantly increase?
Yeah, that's one way to put it. When the volume of a book increases, the weight increases as well. Yep. Another way would be that the density of paper is not 0. So this all kind of makes sense. Down here, we've got some stuff that we probably don't really need. The residual standard error. This is the related to the variability of the residuals. We've got this multiple R squared and an adjusted R squared, and we'll get to what those mean. But you see that they're a little bit different. The adjusted R squared is a little bit smaller. And then finally, we have an F statistic. So it's actually performing an analysis of variance here. This is an F statistic incorporating the amount of variance attributable both to the intercept and to the volume. And it turns out that the variability, or the sum of squares attributable to the intercept plus the volume is much bigger than that to the residual variance. And so we have a big F statistic over 52 and a small p-value, which you'll notice is exactly the same as the coefficient for volume. So in this case, it's equivalent. If we have more variables in here, it would not be equivalent to any one of them. It would be like a test of the overall model and the amount of variance reduction due to the overall model rather than the individual variables. And it's telling us that the variance reduction attributable to this model is not just due to random chance. So there is some significant reduction in variance to this model, or in other words, it's an okay model. So that last plot just had books, but here's a plot where the books are separated into hardcovers and paperbacks. So the hardcovers are these light blue squares, and the paperbacks are these like dark gray triangles. And you can kind of see that the paperbacks for the same volume tend to weigh less than the hardcovers, which kind of makes sense. They have lighter covers, maybe lower density covers. So can you identify a trend in the relationship? I guess I already answered this question between volume and weight of hardcover and paperback books. If I just had to look at this, I would say for hardcover, it looks something like this. And for the paperback, it looks something like this. The slope looks about the same, but it kind of looks like the intercept is different. But let's check it using guess what? Multiple regression. There's the answer. Paperbacks generally weigh less than a hardcover book after controlling for the book's volume. So volume of the book matters. It matters even more than whether it's hardcover or softcover. A large change in the volume has a pretty large effect on the weight. But controlling for the volume, so for two books of the same volume, paperback weighs less. Sound familiar? I don't know if you talked about, does that remind you of anything, I don't know, from your epi class so far about like controlling for the effects of income and age? This is the relationship you see between the exposure and the outcome. It's the same idea as the paperback and hardcover books. The idea is that with a multiple regression, hitting separate coefficients for different things that may contribute to the outcome, you can control for all but one of them. So you fit separate coefficients for each variable, and that allows you to estimate the contribution of each one of the variables while holding everything else constant. Yes?
How can we find parallel lines and that you suggested, but both of the lines should pass in the origin, should pass in the zero, because when zero volume, of course, there will be zero weight. So how can we draw it?
So, question: how could the lines be parallel if they should both pass through the origin? I guess that depends on how the measurement of the width is done. I mean, if it is measured, I mean, for one thing, if you have a hardcover book, you can't, in practice, have zero volume because you still have to have the covers. So maybe they're talking just about the width of the pages, not the covers included. So if that's how you're measuring it, then you do expect at least to have the weight of the covers at 0 volume. I mean, in this case, as in a lot, the intercept is not something that actually occurs in nature. Like, we don't have 0 volume books in the world. So you know, it can be useful to think about it in this case, in that the intercept might provide evidence of how the width is being calculated if we weren't sure, even though we know in real life there are 0 volume books. So it can still be useful to think about as you have. All right, so let's throw them both into a regression and just go ahead and do a multiple regression. And you'll have a chance to do this yourself. But I did it, and it's easy to do in R, it's easy to do in SPSS too. I just threw in cover into the model, and it gave me this coefficient for something called cover : paperback. So here the variable was called cover, and the 2 levels were HC and PB. And I'm getting a coefficient here for PB, for paperback. And that's important in how we're going to interpret this estimate, because the one that we don't see here is the so-called reference group. And so hardcover is our reference group, and paperback is our comparison group. How do we interpret this estimate? This is the expected change in weight for a paperback book compared to a hardcover book of the same volume. So holding volume constant, we expect a paperback book to weigh 184 grams less than a hardcover. Now, there are ways you can choose your reference group, and we could have chosen paperback as the reference group and gotten a coefficient for hardcover. What do you think this last line would have looked like if I had used hardcover as my, or if I had used paperback as my reference so that there was a coefficient instead here for hardcover? What would this bottom line look like?
Opposite signs.
Yeah, the sign would switch on the estimate. This would be a plus 184. And everything else would be identical. Except for the t-value. The t-value would also switch signs. The standard error and the p-value would be the same. So again, you see that there's this adjusted R squared that's a little bit less than the multiple R squared. And you see this F statistic with a p-value that is now quite a bit smaller than either of them. Well, no, it's not smaller than any of the p-values here. It's kind of similar, a little bit bigger to the p-value for volume. But this, again, is for the overall model. This is telling us that as a whole, the model provides a statistically significant decrease in the residual variance. If this p-value were instead, 0.4 or something, it would mean that the amount of reduction in residual variance from the model is equivalent to what you would expect with no relationship between either of these variables and the outcome or the weight. So this model is nice because it gives us now a couple things at once. It gives us the relationship between volume and weight, it gives us the relationship between the type of cover and weight. It tells us how much, on average, hardcovers weigh more than an equivalent softcover book. So maybe if you were building a library and you needed to estimate the weight, this would be useful. And it tells us that that a lot of the variability, so even more, remember before our R² was 0.8, now it's 0.9275. So like 93% of the variability in book weight can be explained by their volume and the type of cover. The rest, we don't know where that variability comes from. How much ink is in it, maybe. Yes?
If the p-value is bigger, and we will accept the null hypothesis. So
If the
the
p-value
lines,
is big enough, you would accept the null hypothesis.
yeah.
Yeah.
So the lines will be parallel as well to the x-axis, or they will be so much different. I mean, no parallel at all.
So it's a good question. What about are those lines parallel? The question you asked before. In fact, I still don't know. I have to add an interaction term to this to make some kind of inference on whether these lines are parallel. I'm assuming here that they're parallel in this model because they have this intercept. Paperback, we would subtract 184 from the intercept, but we do not change the coefficient of volume. So essentially what this model is doing is it is giving a different intercept for hardcover and paperbacks, but the same slope.
Yes. So I mean, if the p-value is big, so there will not be any parallel relationship. There will be, I mean.
So like if the p-value for cover type was big?
No, for the model.
For the model overall.
Yeah.
So if the p-value for the model is overall, that means that neither volume nor cover type are associated with book weight. So it means that our data are they're consistent with volume, so with both being horizontal lines. The intercept could still be positive, but the coefficients of volume and cover type are 0. And so the slope and the shift between those lines would be 0. Both of them would just be horizontal lines.
The x-axis. Parallel to the x-axis.
Parallel to the x-axis. That's right. Our data would be consistent with that. Doesn't mean we've proven that there's no relationship, that the density of paper is 0, but it's small enough that we don't have any evidence of a non-zero density or of a non-zero cover weight. Okay, this one's easy now because I've given you the answer already. Based on the regression output below, which level of cover is the reference level? And note here that PD means paperback. So what is the reference level of book type? Hardcover, very good. Which of the below correctly describes the roles of variables in this regression model? So A, the response's weight. Explanatory variables are volume and paperback cover. You can take a peek at the other ones if you want. So 3 out of 4 have book weight as the response, and then they differ by what the explanatory variables are. Okay, so first, what's the response variable? That's easy. We can eliminate one here. Yeah, response is weight, so let's get rid of that. So then all of these have volume as the predictor. This one has cover type as a predictor, and that's not strictly wrong. It's just, it's not specific. It's not as specific as up here, so I'm going to eliminate it. It's not wrong. So, you know, cover type is a predictor, but more specifically, because we fit an estimate for paperback covers, yeah, A is the right answer here. B is definitely wrong because we have not fit a coefficient for hard covers. We fit a coefficient for paperback covers. I'm not crazy about this question because D is not exactly wrong. It's just not specific. It's not as specific as A, so it's not as good of an answer. So it's pretty clear now, I hope, that we can make inference on the relationship between predictor variables and the outcome from those regression tables from the coefficients. So how about how to make predictions? So it's one thing to understand what the relationship between volume and cover type is on the weight of the book. That's nice. But it's another thing, and maybe something that you also want to do, to actually predict the weight of a book from our model. This table is telling us a formula for doing exactly that. And the model is that our predicted weight, I'm putting this hat over the weight to say this is a prediction, is equal to the intercept, 197.96, plus 0.718 times the volume in cubic centimeters, minus 184 if the cover is paperback. Cover is hardcover, then just don't do this. So there is a formula for calculating or for predicting the weights of books based on this model. Nice, right? So yeah, this is an indicator variable, this cover colon paperback. So it's 1 for paperback books and 0 for hardcover books. The so-called indicator or dummy variable. And we always use those in fitting models. If you're doing it in SPSS, you'll see that there's 0, 1s and they just have labels. It's something similar to that in SAS, in that you have to explicitly code these dummy variables as 0, 1s, but you can label them. It's a little bit different in R in that you'll just see the labels, and dummy coding can be done automatically for you. So, and for paperback books, because we see PB here, the indicator, the dummy variable is 1. So there is how we calculate, or we estimate the weight of any given book. Visualizing it, like I mentioned, we are assuming that these lines are parallel. We haven't allowed in the model the possibility of different slopes. So they are 2 different lines which just differ in a shift or in the intercept by the amount of that coefficient for paperback books. maybe this is a little repetitive now, but I feel okay about it since you had the online class last week, and I know perfectly well that not everybody watched it. So just to walk through again the interpretation of these coefficients, the intercept here would be the weight of hardcover books with 0 volume, and that's expected to be 197.9628 grams. So this is a hardcover book with 0 volume. So maybe that is the weight of the cover, and it's actually statistically significant now. So we're saying that we expect books with 0 volume to have a positive weight if they're hardcovers. So it does imply that maybe the measurement is just of the pages. Maybe it doesn't include the book or the cover, which would make a certain amount of sense. Maybe the density of covers is different than pages. So the slope for volume tells us that with all else held constant, so for either a hardcover or for a soft cover book, if it weighs 1 more cubic centimeter, it tends to, or if it has a volume of 1 cubic centimeter greater, it has a weight of about 0.72 grams more. And this estimate for the cover tells us that with volume held constant, that paperback books weigh 184 grams less than hardcover books. So let's see, prediction. Which of the following is the correct calculation for the predicted weight of a paperback book that is 600 cubic centimeters? And the table is just here for your reference. So take a quick look at these and tell me what the answer is. As soon as you're feeling confident, put 1 for A, 2 for B, 3 for C, and 4 for D. So far, I see 3 different answers. Don't worry, I'm not keeping track. You don't have to feel. Okay, I see 1s, 2s, and 3s. Okay. So well, I'll have to figure this out myself now.
I say can change it.
So the slope is 197. So I suspect that it's A, C, or D, starting with the slope, plus 0.72 times 600, so those all look right. So far, let's see, I've eliminated, I think, B and D. And then it's paperback book. It's paperback, so minus 184 times 1. So I think it's A. Anyone disagree? I could be wrong. I make mistakes all the time. I think that's it, though. All right, so books are a great example, but what about something public health related? Don't have I do have the data and some actual plots from this. An example of modeling poverty where the response variable is the percent of residents who live below the poverty line, and this is for regions, maybe for census tracts. I'm not sure what the actual, whether it's counties or census tracts or zip codes, but the predictor variables It's clearly for various regions are percentage of residents living in metropolitan areas, percent self-reported as white, percent who graduated from high school, and percent with a female-only head of household. And the observations, sorry, it's right here, right, are all 50 US states and the District of Columbia. So this is just state level data. Kind of a nice exploratory scatter plot. This is taken from the textbook. Unfortunately, I don't think you can do this exactly like this in SPSS, but what this is plotting pairwise scatter plots for each of these pairs of variables. So poverty being our response variable and our 4 predictor variables, we're getting scatter plots for every possible pair of those variables, along with the Pearson correlation coefficients that are sized to be proportional to the magnitude of the correlation. So we see right away here the largest associations. There's one. The largest association for our response variable poverty is minus 0.75, and that is with the percentage of high school graduates. So as the proportion, you can see the slope is negative here. It's telling us that as the proportion of high school graduates increases, the percentage of residents living in poverty decreases, and that's quite a strong relationship. There are some other ones here too. There's a positive relationship with female-only heads of household. So there tends to be, with more female-only heads of household, more poverty. There's another couple pretty strong relationships between the percent self-reported as white and the percent female heads of household. Looking over here, they're in areas with a high proportion of female-only heads of household. There tend to be fewer self-reported white. So the reason I'm showing you all of this is to start talking both about multiple regression in another more of a real-life public health application, and also to start talking about collinearity. Collinearity is something that happens when you have correlation between your predictors, and that is exactly what is happening here. We're seeing that for a couple of these, especially for female the percentage of female heads of household, that is pretty strongly negatively related both to high school graduation rates and to the number of self-reported whites. And these are those two plots. So where you have a lot of female heads of household, you have fewer high school grads and fewer self-reported white residents. So the challenge that this is going to raise, you can imagine, is where you have such a strong relationship between two of your predictors, it's going to be hard to distinguish between their effects through a regression model. So, you know, in this case with poverty as an outcome variable, where you see it negatively associated with high school graduation and positively associated with female heads of household, it's going to be hard to say which of those it is, or if it's some intertwined effect of the two, because they're so strongly associated with each other. Based on this data, it will be potentially hard to distinguish them. We will try with a multivariate model because it does give us the opportunity to estimate the effect of one of the predictors holding everything else constant. But when you have really highly collinear predictors, it's hard to make those estimates, and they tend to be inaccurate estimates. Yes?
But here, in the example of poverty and white, we can say who's the main predictor, as because poverty doesn't make people white.
Right. So in terms of but you're talking about the relationship between the response and a predictor. So it's clear that there's only one direction that causality could go. But what I'm saying is that because whiteness is so strongly correlated with female heads of households, it could be hard to say which of those variables is more directly along the social causal pathway. Without, I mean, from the statistics, it could be hard to tell. You would have to go to other arguments or other data. Very good question, though, and that gets at why you spend time drawing these directed acyclic graphs to think about what the possible causal pathways are and what you think they might be. And in that case, clearly you're not going to draw a line from poverty to self-reported race. So just going to, with the simple linear regression between poverty and the percent female householder, we get this strong positive slope. And let's see, a correlation of 0.53, does that agree with, yeah, that's what we had on this previous page between poverty and female householders, 0.53, and an R-squared of 0.28. Going back to R-squared, there are 3 ways to calculate it. One, as I mentioned, is just the square of that Pearson's correlation coefficient between the 2 variables. Another way is to square the correlation coefficient between your actual y's and your predicted y's. And the third is based on its definition of the explained variability in y to the total variability in y. And these 3 different ways, I'm mentioning them now because it's important to know these different definitions when it comes to multiple regression. You can use any of these for a simple linear regression, but you can't use all of them for a multiple linear regression. Specifically, you can no longer use one anymore for multiple linear regression.
You mean no longer because of the last slide? Like
because there's no longer just one x, you have multiple x's, so there's no correlation coefficient between x and y in a multiple linear regression. Yes?
But you will get different values of those?
No, for a simple linear regression, you can use all 3 of these and get exactly the same value. Yeah, all equivalent. But for multiple linear regression, you can only use 2 or 3, because no matter how many predictors you have, you can calculate a predicted value for each record, and you can also calculate this explained variability. Using an overlay. So let's go ahead and do it. This is just for the simple linear regression, and I'm printing out here an ANOVA table. If you performed an analysis of variance, which you can do for a continuous predictor, not only for a categorical predictor like we did it. And you can get an analysis of variance table like this with our sum of squares, mean squares, and F value. So the sum of squares for y here, which is just the each observation minus the mean, or the expected value, is 480. This bottom one. This is just the well, it's the variance times the sample size. So we get this total sum of squares from an ANOVA table. We also get the sum of squares of residuals. It's a line right here on the table of 347. So we've got now our total variability, our unexplained variability, and the difference between them is our explained variability. So from this ANOVA table, you can calculate your R squared value. (132 over 480) gives us that same value that we had of 0.28. So why bother? Just as I meant, I'll just mention again that you have fewer options for multiple regression than you do for simple linear regression, but any way that you use is going to give you the same R squared. So let's move ahead here to, I'm going to try to finish up a little soon here. So I'm putting in two variables now, both percentage female heads of household and percent white, into a multiple linear regression. And so I have estimates for both of them, and I have p-values now for both of them. And based on this, I can see that controlling for the percentage white of white respondents, there is still a significant effect of female heads of household. So it would seem, based on this, that that the percentage of female heads of households is the stronger predictor. And looking at the ANOVA table, you see that the sum of squares for the predictions from female heads of householders is larger, so it means that more of the variability is being explained by percentage female heads of house than percentage of white residents. Yes?
So how can we explain the p-value of white, 0.29?
So this p-value of white is saying that after controlling for the percentage of female heads of household, we're not seeing a significant relationship between the percentage of white heads of percentage of white residents and the percent living in poverty. And this is probably because some of the poorest states in the U.S. are both majority white or large numbers of non-white respondents, but there are in the South, looking state by state. Based on my limited understanding of American geography, but I understand that the southern states tend to be the poorest. So our calculation now of R squared Again, explained over total variability, but I'm adding in these two, 132 plus 8 into the explained, and still this total on the denominator. So even though this is not a statistically significant coefficient, the coefficient for white, it still adds something to the sum of squares. The predictions, we're never probably going to have a coefficient or an estimate of exactly 0, and as long as it's not exactly 0, there will be some variability associated with that variable. And so any time you add a variable, whether or not it is related to the outcome, it's going to add something to this numerator of explained variability, and it's going to increase your R squared. So you can just keep on adding irrelevant variables and keep on increasing your R squared until eventually you get up to 1 if you add enough variables. Which sounds problematic, right? Not very useful. We'll get to the solution. So as I mentioned, these two explanatory variables are somewhat collinear. And you can tell this in the table. So, or in these regression tables, first for the univariate regression on female heads of household, and then for the multiple regression. Looking at the standard error here of 0.16 in the univariate, look at this. It increases in the multivariate regression. And that is something that happens when there's collinearity present. If these were independent variables, this standard error would stay pretty close to the same. Not exactly, but pretty close. And the stronger the collinearity, the more this is going to, the standard errors will increase in the multiple regression. So what happens when standard errors increase? These t-values go down and the p-values go up. So when you have collinearity, what is going to tend to happen is you can still get estimates for each variable, but their sampling variability is going to increase a lot, and it will be hard to reject the null hypothesis. So it's because these predictors, the more highly correlated they are, like if there was a correlation of 0.99 between these variables, or if they were, even if one was categorical and the other was continuous, but they're very highly related, you would get very large standard errors, which means that if you repeated your study, you get a very different estimate of these coefficients. And that is because it is just very difficult to disentangle contributions of these two highly correlated variables. So that's what it means to be collinear. They're correlated predictor variables. They're independent. If they're not correlated, at least in the population. And ideally, we would have predictors that are independent of each other. And it's actually, when you do find you have highly collinear variables, there are ways you might decide only to include one of them in your model because you decide that they're too closely related to each other, either by just arbitrarily picking one of them, or sometimes people do principal components analysis to reduce them down to orthogonal or non-correlated variables. So it's something that you can't avoid usually in observational data, but is not something that you see in experiments or clinical trials most likely. There have been some interesting papers about observational data sets that, in fact, at least a low level of collinearity is really widespread. Like you can have something like the National Health and Nutritional Examination Study, NHANES, and you have hundreds of observational predictor variables, and they're all correlated to each other. And so in that kind of a situation, it is very hard to say, to make causal inference on individual variables. Or you can, if you pick any one of them, you can see a relationship with an outcome, and then pick any other one and also see a relationship with the outcome. So just keep in mind collinearity is something to check for if you're doing multiple regression. You have multiple predictors in a model. So I mentioned that R-squared has this problem that the more variables you add, the more it goes up, even if those variables are totally unrelated to outcome. There's a solution called this adjusted R-squared that penalizes your R-squared for additional degrees of freedom used by your model. And in the adjusted R-squared, as you add variables that are not related to your response, it does not increase. It only increases for variables that actually help you to predict the response. So R-squared and adjusted R-squared are really about how well you predict the Ys. Here's the formula. That's fine. I'm not going to make you calculate it. Just know that it's always smaller than R-squared. Unless you're adding a lot of variables, they won't be too different from each other, like you saw in these multiple regressions with 2 variables. But if you have 10 predictor variables, then the adjusted R-squared can be quite different from the raw R-squared. If you're using them for model selection, you would tend to choose models with a higher adjusted R-squared. So wrapping up, I want to make the point that multiple linear regression is a so-called additive model because, for example, when we were interpreting the coefficients of book volume and cover type, they added things to our predictions. But not all models are additive. When you get into logistic regression, log linear models, these are things like Poisson count models and negative binomial count models. Those are multiplicative, and the coefficients actually multiply your predicted odds ratios or rate ratios in those types of models. So as you get into logistic regression next semester, just keep that bug in your ear that it's a multiplicative model, whereas what we did was an additive model. Watch out for collinearity and remember R-squared. I put in a little summary here just for you on your last slide of all of these different kinds of things that we did that might help you to choose tests if you're a little unsure for your final project based on the types of variables that you have and the type of comparisons that you want to make. And I even put in some things here that we haven't covered, so-called non-parametric tests. You don't have to use them, but you should probably be aware that they exist. They are equivalents to the things that we have done here, but without making assumptions about normality or any assumptions about the distribution of variables in the population. And any questions before we'll take a break? I'll hand it over to Tony to do the lab. I'll go try to dig up an easel for our one presentation so that we don't have to just lay it out on the table, and we'll do that maybe right before the end of class. Okay, thank you.